Hi, my name is Catherine Hewer Ratliff. You can see here. And today's date is December 19th, 2019. So today I'm going to be talking about the anatomy and enzymology of fat absorption. So when we think about dietary fats, the primary dietary fat that's found in foods is triglycerides, and these are composed of a glycerol molecule and 3 fatty acid molecules. Now these fatty acid molecules can either be saturated, meaning they have no double bonds in the fatty acid tails, or they can be unsaturated, which indicates the presence of at least one double bond in the tail. These are going to have different functions within the human body, dependent on the number of, the length of the carbon chain, as well as the number of double bonds that are present in that chain. Triglycerides can also be classified by their chain length and start with short chain fatty acids, medium chain short chain triglycerides, medium chain triglycerides, and long chain triglycerides. And again, these are all going to be digested slightly differently, as we'll see as we progress through in this presentation. So in addition to triglycerides, there are also other lipid molecules that are absorbed in a similar way as triglycerides. And these include cholesterol and fat-soluble vitamins. And this will be important to consider as we think about our case study at the end of this presentation. So here's an overview of the digestion and absorption of dietary fats. So as we can see here in this slide, digestion begins in the stomach with the addition of gastric lipase. Now gastric lipase is an enzyme that will hydrolyze the bonds between the glycerol molecule and the fatty acid, releasing at least one free fatty acid, if not two. So the end product that we get here is either a monoglyceride, occasionally a diglyceride, and then free fatty acids. Gastric lipase has a preference for both short and medium chain triglycerides in comparison to pancreatic lipase, which will hydrolyze all different forms, chain lengths of triglycerides. So we will be discussing this again in our case study later in this presentation. So what occurs here is the partially digested lipid molecules then are going to travel into the chyme and into the small intestine, where the majority of dietary fat digestion and absorption occurs. So here we have the addition of biosalts and pancreatic lipase that are going to work together to digest and break down the triglyceride molecules into the free fatty acids and the monoglyceride molecules, which are then able to be absorbed into the enterocyte of the small intestine. So we will explore these processes in a little bit more detail as we go. All right, so as food moves throughout our digestive system, and specifically when we think about fats, we have what are considered fat droplets that move from the stomach in the chyme after the initial digestion with gastric lipase. Now these fat droplets, due to their size, have less surface area for enzymatic digestion to occur, and that is why we have the additional digestive assistance from bile salts in addition to the different enzymes. So bile salts are produced in the liver, stored in the gallbladder, and then released into the small intestine. And they are considered amphipathic, which means that they have both hydrophobic regions, which interact with the surface of the lipid droplet, as well as hydrophilic regions, which interact with water. And what this does is it creates almost like a chemical detergent, which creates a lipid emulsion, and it allows for the interaction of the digestive enzymes, the pancreatic lipase, with the triglycerides that are still present within the fat droplet, breaking them down into these smaller fat droplets in which these enzymes can work more efficiently and allow for the further breakdown of these triglyceride molecules. Now, the pancreatic lipase and glycolipase are also involved in this set of steps of the intestinal digestion. Pancreatic lipase, as the name implies, is released by the pancreas, and it works to cleave the triglycerides into 2 fatty acid molecules and 1 monoglyceride. Co-lipase is also an important piece here because, as you can imagine, in this emulsion of biosalts with the triglycerides, there's not a lot of space for the lipase to work. And so the co-lipase has 2 different functions. One, it helps to displace some of the bile salts, which allows the lipase to access the triglycerides. And it also anchors lipase to the bile salts in order for it then to continue to work within this lipid droplet. All right, so what we have here at the end of this process are more monoglycerides as well as free fatty acids. These then combine with phospholipids, cholesterol, fatty acids to form what's called a micelle. And this micelle then transports all these lipid molecules to the brush border of the small intestine, where they will then be absorbed. So here we have 2 different images that depict the absorption of dietary fats. So as we can see in this image to the left here, we have a micelle. And what happens at what's considered the brush border, which is this area of the enterocyte of the small intestine, the micelle releases the free fatty acids and the monoglycerides. And these are able to cross the intestinal cell through simple diffusion. Cholesterol and phospholipids also pass through. However, cholesterol is transported into the cell in more of an active process. Now, once these molecules are within the enterocyte, the fatty acids and the monoglycerides are transported to the endoplasmic reticulum, which we see here in this diagram to the right. Within the endoplasmic reticulum, they are then packaged up to recreate triglycerides, and then they are moved from the endoplasmic reticulum to the Golgi apparatus, where they are combined with proteins, cholesterol, and phospholipids into what is considered a chylomicron. And these chylomicrons, which contain all of these different components, then are transported out of the cell via exocytosis, where they then enter the lymphatic system via the central lacteal, which we can see here in this diagram. Now, glycerol molecules, we discussed that in the previous slide here, that fatty acids and glycerol molecules are both part of what creates a triglyceride. Glycerol molecules, because they are not hydrophobic or not lipid soluble, they are hydrophilic. They can be transported and travel directly in the blood capillary here. So once our chylomicrons are transported out of the cell via exocytosis, transported into the lymphatic system via the lacteal, they are then transported to the liver where further processing occurs. So here is a summary slide of both the enzymatic, and I also included the biofacilitated digestion that occurs with fat digestion and absorption. So as we discussed above, this starts with gastric lipase, and gastric lipase is produced by the chief cells, and its primary function is the enzymatic breakdown, or what's considered hydrolysis. And what we discussed earlier is that gastric lipase has a preference for both short and medium chain triglycerides. The resulting product of gastric lipase is fatty acids, monoglycerides, and some diglycerides. The next step of fat digestion, as we discussed, is in the intestinal phase of digestion, and this involves the last 3, colipase, bile salts, and pancreatic lipase. We're going to skip down here to the bottom to bile salts, where we'll discuss this first. So as we discussed earlier, bile salts are produced by the liver, stored in the gallbladder, and then released into the small intestine, where they function as a chemical detergent which helps to emulsify the lipid lipid droplets. As a result, we have an increased surface area for the digestive enzymes to work and to enhance the digestion of dietary fats. Next, these two enzymes that are involved include colipase and pancreatic lipase. Now, colipase is also released and produced by the exocrine portion of the pancreas, and interestingly enough, it is released as a zymogen, so an inactive enzyme. So in the case here, it's called procolipase. Within the small intestine, it's activated by trypsin, which we know is also very much involved in the digestive processes and the digestive enzymes that are involved in the small intestine. Now, colipase, as we discussed, helps to anchor lipase to the bile salts on the lipid droplet, which allows for greater access of the pancreatic lipase to the triglycerides. So we have an increased efficiency of pancreatic lipase and an enhanced enzymatic digestion as well. Now, pancreatic lipase is also produced by the exocrine portion of the pancreas, and its role is also similar to gastric lipase, the hydrolysis of triglycerides, here cleaving at what's considered the SN1 location. So if we're thinking about a triglyceride molecule, you have the glycerol backbone and then the 3 fatty acids here. So it would cleave the first one and the third one of the triglyceride. So our end result is fatty acids, monoglycerides, and occasionally if it just cleaves one, then you also get a diglyceride as well. So this concludes our discussion on the enzymatic physiology of fat digestion and absorption. So next we are going to go to our case study here where we will explore and apply these concepts to a specific situation. So orlistat is a medication that has been used to as a part of a treatment for individuals with obesity. It works as a potent inhibitor of gastric and pancreatic lipase. And so what we want to explore here is what impact, given that it inhibits these two enzymes, what impact it has on lipid digestion and absorption. So my first question for you is, what effect would orlistat have on dietary fat digestion, and how is this used in individuals with obesity? So as we discussed, orlistat inhibits these two enzymes, which means it's blocking the enzymatic degradation, digestion of digestive fats, dietary fats. So since triglycerides are not broken down, they likely are going to be excreted in the stool. There's going to be less that is absorbed, and then that is going to potentially impact the amount of the caloric energy that an individual would absorb or take in through the intestines into the bloodstream, which could potentially help to lower weight. So one possible side effect of orlistat is a vitamin K deficiency. I'll explain why. So here what we're thinking about is, as we discussed at the beginning, there are fat-soluble vitamins that are also absorbed in the similar process that we discussed with triglycerides. Since orlistat inhibits the gastric and pancreatic lipase enzymes, it could potentially impact the digestion and absorption of fat-soluble vitamins such as vitamin K, therefore creating a deficiency. So what are some of the possible digestive side effects of this medication? So if there is more fat that's not being absorbed, there's potentially more that's going to be excreted in the stool, which could cause steatorrhea, loose stools, diarrhea, or abdominal cramping. And then lastly, what would happen if this medication was specific to only pancreatic lipase, and how would this influence the types of triglycerides digested and absorbed? So if it's only pancreatic lipase, that might mean that there's gastric lipase that's still functioning. As we discussed, gastric lipase has a preference for short and medium chain triglycerides, so potentially we might see more short and medium chain triglycerides digested and absorbed compared to longer chain triglycerides. This concludes my presentation. I have included the references here to cite the resources that I used, and I welcome any questions. Thank you.